Don't tell me I have to do my dash of banter again. I'm scared.
A dash of banter.
A sprinkle of wit.
Of comedy.
Like Salt Bae. Yeah. That's right. Banter machine.
Welcome to Absolute Gene-ius, a podcast series from Thermo Scientific. I'm Jordan Ruggieri.
And I'm Cassie McCreary. And today we are joined by two more resident Thermo Fisher scientific geniuses, Dr. Min-Jin Kim and Kimberly Gomez.
Kim has worked for Thermo Fisher Scientific since 2020, and Min-Jin has been with us since 2022. They specialize in all of Absolute Gene-ius's favorite topics: digital PCR, AAV viral titers, lentiviruses, and much more. We had a blast talking with them and hearing some incredible stories from their work, and we hope you do too. Min-Jin and Kim, thank you so much for joining us today on Absolute Gene-ius. We are very excited to have you. We hope you're excited to be on as well. Can you start by giving us a little bit of background about yourselves and including what you currently do at Thermo Fisher Scientific?
My name is Kimberly Gomez. I'm a scientist at Thermo Fisher Scientific. I work a lot on qPCR and dPCR reagents, and right now I've been working on a lot of assay development specifically for biopharma and even more specifically cell therapy assays.
My name is Min-Jin Kim. I'm a scientist in Thermo Fisher Scientific as well. I also work in the dPCR, qPCR. My focus is more so on the digital PCR than the qPCR, where I do a lot of digital PCR assay development, both in duplex, singleplex, but also in multiplexes, as well as help troubleshoot and provide support for those who are in need of digital PCR.
So, talking about, biopharma and pharma assays, one thing that has come up in some of our other conversations are around AAVs and LVVs. Can you give a little bit of background? What are those and why are they useful in research workflows today?
Sure. AAVs are adeno-associated viruses. LVVs are lentiviruses. And these are two vehicles for being able to deliver genetic material to subjects. The idea is that with this genetic material, it could help with different conditions and diseases. And right now, they're being used in gene therapies.
To add on that, so basically, it's a summary of trying that there are other genetic mutations or some genetic changes that might happen in the body, and that could lead into certain diseases. In that case, some of them can or may be treated by other methods, but some of them, it's not really applicable. So in that cases, we are trying to use these AAVs and LVVs to transfer the non-mutated and non-changed genome of interest into the subject so that they may have the unaltered proteins or unaltered state so that they may be healthy.
Well, very interesting. Sounds really, really exciting, actually. What makes AAV and LVV such good delivery systems? Or is there a reason why these are preferred viral vectors?
Short answer, it's safe, but I'll let Kim elaborate on that.
Sure. I know more about AAVs. There are a lot of serotypes for AAVs, and it helps in being able to target specific tissues in the body. Another reason is that there's lower immunogenicity. So that would mean, like, even if you're receiving this virus, it's a foreign body. Your body's going to try to look for it and see it as it's a virus and it shouldn't be there, but because it doesn't have as much of a immune response compared to other viruses, then it could bypass our own immune system for a while before it gets a response and gets and your body does the natural thing to get rid of it in your system.
LVV is the same reason that it's being used commonly for cell and gene therapy. LVVs and AAVs do have high efficacy in delivering these genomes into the subjects than other viruses. And that's probably why it's most commonly used.
Yeah, interesting. So it sounds like it helps to deliver a little bit more accurately, right? With the right cell types and the right serotypes and also kind of evade the immune system so it doesn't kill off all the delivery systems before it's able to actually have some type of effect. Are there particular sizes, or does size have anything to do with how effective these vectors are? Can you give a little bit of information around what size genes maybe can be inserted, or anything around the genome of those vectors and viruses?
It's actually an interesting question because I think that as the technology is advancing, usually the limit for AAVs has been found to be like 4.5 or 5 kilobases of DNA, but I've seen more and more people finding ways around that and adding in longer sequences of DNA. So hard to say. I think there's always something new coming out with gene and cell therapy, and the advancements, I feel like it's just exploding, and there's a lot more to come in the coming years, I think.
Traditionally, for AAVs, it's about like 5 kilobase pairs that you could put into the vector itself. So that would leave you, usually the gene of interest and whatever that's in, it's around 100 base pairs, maybe up to 500 base pairs-ish for gene of interest. The other carriers would be shorter than that, obviously. And for LVVs, I believe it's a little longer, to around 9 or 10 kilobase pairs, just because it's a little bit larger viral vector. But it's also the same concept where the other carrier DNAs or genes would be in a shorter fragment, where the gene of interest could be like about kilobase pairs or whatnot. But there are advancing technologies, and as current technologies keep on advancing, people have found ways to squeeze in more gene material somehow, which I am not familiar of at this point. I think Kim is also being exposed to that new technology as recent. So that's something that we could look out and see if that changes anything on a digital PCR system versus qPCR, as well as if we could get more insight on whether using these longer genes and packaging them would have an efficacy on the treatment itself.
Talking about these vectors, can you give an overview of maybe a common cell or gene therapy research workflow? How do you go from virus to actually taking that and conducting research within a subject?
To be fair, we don't conduct research to the subject. We observe them for a longer time. But to give a high-level overview, it's just basically you make your virus inactive. Of course, you don't want the virus to be actually infecting you. And then you would want to have a host cell that could make these genes, and then you make these capsids. And once that is done, you go through a bunch of different processes. I think it's 7 steps, which is all outlined in our webinar, which Kim kindly presented on.
Kim, is there any like really critical step that maybe stands out over some of the others? Maybe we can focus in on what 1 or 2 of those really critical steps kind of in between virus to injection.
Sure. There are a lot of testing that's done between creating that virus and putting it into the subject. One of those would be viral titering, making sure that the amount of your virus is what you expect in that concentration. And as you're going through the different steps of the production, you want to make sure that you're not losing any of that virus. So vector genome titering happens really often within that process.
Why is it important to know exactly what concentration you're working with and be able to utilize that through the manufacturing process?
There are several reasons, one of which you don't want to lose your virus as you're making it. You want to make sure that as you're cleaning it up, as you're polishing it, getting rid of any of the contaminants, you want to make sure that you're still retaining as much of the virus as possible. The genomic titering is one way to look at the characteristic of AAV. The genomic titering is specifically looking at the DNA component within the capsid of the virus. And that's really the genetic material that you want at the end. As long as you're keeping track of how much of that DNA content is in your virus, then you have a pretty good idea of how much of your total virus is in your sample.
Interesting. When we actually talk about viral titers and even this entire workflow, are there common technologies that are used to make sure that you have an accurate concentration of virus?
The gold standard for a long time was qPCR for vector titering, but I think there's been a really big push for dPCR in the last couple of years. I think regulatory bodies have really seen that dPCR has that really high consistency and reproducibility. So a lot of gene therapy companies have started to use dPCR in place of qPCR. And it really shows with a lot of the literature that's out there nowadays surrounding gene therapy. I think I've seen more people use dPCR for that absolute quantification of DNA.
Can you talk a little bit about some of the advantages of digital PCR over real-time qPCR for this type of research?
Sure. With qPCR, you would usually run a standard curve. You would make a dilution series and run that alongside your sample of unknown concentration and derive your concentration from that standard curve. Big issue with that is sometimes your standard curve could be made from reference material, so a different AAV, or it could be made from a plasmid. So a lot of the preparation in making that standard curve can really affect the concentration that you derive from that standard curve. Another thing to consider is that with qPCR, it's not as robust against inhibitors. We see with dPCR that we have a lot more robustness with different matrices. So that's a big advantage, especially when you're pulling your sample from different points of from production of the virus.
So basically, the summary would be like for qPCR, although it is like very commonly used and everybody nowadays, in our field at least, knows how to use a qPCR, but there are limitations on requiring a standard curve like Kim mentioned, which may affect and impact the actual results accuracy and precision. Another one is the inhibitory effects that is more prevalent in qPCR than digital PCR just because it's in a more bulk sample prep situation. In that case, sometimes for AAV applications, you would pull samples from different stages of the production, and which would include different proteins, different buffers, which have different inhibitory effects. In that case, qPCR would be a little bit more limited into neglecting or mitigating that effect as opposed to digital PCR. And also for precision-wise, it is recommended for qPCR to do at least a triplicate of your sample, which increases the sample volume. Digital PCR, especially our Absolute Q, we do have lower sample volume input as well as almost no dead volume, which helps preserve your samples. On top of that, since it is an absolute quantification, it technically, in theory, does not require any replicates to be run. So you could run your one sample in one array. Another advantage is that there are some other analysis that you could do on digital PCR that you can't on qPCR, but it's about the molecular integrity of the gene of interest that is being delivered to the subject.
We can talk a little bit about molecular integrity. This is a topic that's come up and with a couple guests before, but Min-Jin and Kim, in your experience, why is the intactness of that molecule important? Especially in this light when you're looking at cell and gene therapies.
Again, for me, it's the short version because you want the right thing injected to you, not the wrong thing. But Kim can elaborate on it.
Yeah, to Min-Jin's point, you want the right genetic material in those viruses when they're being administered to the subject. A lot of times when there's erroneous DNA that happen to be encapsulated in those viral capsids, they could cause more immune responses. So that's opposite of what we would want. A big part of molecular intactness is making sure that your intended genetic material is in that virus. So the idea is to look at different parts of that DNA, and there are calculations you could do to make sure those targets are linked together on the same DNA strand.
That's incredible. And is that something that's unique to digital PCR? Unique versus, like, say, a real-time PCR?
Honestly, I've thought about it, but I don't see a way that we could do the intactness study on qPCR. I don't know if Kim has different thoughts, but because you're trying to see if they are linked or not, which you will have to go down to a single molecule level, which in qPCR, it is difficult since the samples are not divided into many tiny little reactions. That's why it is possible to do that in digital PCR, just because digital PCR allows you to do single molecular analysis.
I have one more question, and then we get to pass you over to Cassie for her to grill you about your careers. What about labs and biotech pharma labs that need to scale up? Are there automatable solutions out there for digital PCR?
There are automated solutions available. Our autorun would be an automated solution for cell and gene therapy. Our autorun gives you a little bit more confidence that you won't be risking all your plates if you go with 60 or 80.
Yeah, makes a lot of sense. Tim, anything to add on autorun?
Our reproducibility study with 60 plates, we prepared everything before the weekend and we just let autorun do its thing over the weekend. So we were able to see that from time 0 to time 72 hours, consistency across the board. We didn't see any drop or change in signal and fluorescence between that first plate and that last plate. So that really told us that the stability of our samples was held throughout that whole time we were running autorun for over the weekend. So if your workflow consists of high amounts of samples, you can be confident with autorun that as you're leaving the lab to do your thing, go enjoy your weekend, that you're going to have your results when you come back on Monday.
Taking a quick break from our conversation to tell you about Applied Biosystems Quant Studio Absolute Q dPCR system. This instrument enables quantification of your targets without the need for standard curves in only 90 minutes. Digital PCR can be as simple as preparing your samples, loading onto the plate, and running the instrument.
Unlike other digital PCR systems, the Absolute Q dPCR instrument does not use emulsion or other droplet-based methods to compartmentalize reactions. In fact, the microfluidic array plate technology enables consistent delivery of more than 20,000 microchambers. It's a great solution for anyone looking to quantify gene targets.
And Thermo Fisher Scientific has a suite of dPCR assays for applications like AAV viral titer quantification, liquid biopsy analysis, and wastewater surveillance. You can learn more at www.thermofisher.com/absoluteq or visit the Absolute Gene-ius webpage. Again, that's www.thermofisher.com/absoluteq or visit the Absolute Gene-ius webpage.
The Applied Biosystems Quant Studio Absolute Q dPCR system is for research use only, not for use in diagnostic procedures. Let's get back to our conversation.
Okay, party time. That's right. Welcome to Cassie's Career Corner, where we just sit here and we talk about your career and kind of your education, and we don't all have to think very hard. So, Editor Matthew, intro music here. I told you, we're time to party. So, can you both please provide us with just a very high-level, quick summary of your academic studies and your career sort of to date?
I have a bachelor's degree, Bachelor of Science in Material Science and Engineering back in Korea, Yonsei University. Afterwards, I worked at a governmental institution called Korean Institute of Science and Technology until I came here to the States to pursue my doctorate degree in Texas A&M, College of Medicine for medical science. I just wanted to do that because what I'm currently doing right now is trying to develop more biotech tools that people can use to advance biotechnology and, in general, hopefully healthcare and the safety of people. So with the engineering degree, I thought it was not enough, and I thought I needed a background in molecular biology and the medical science of it if I would really want to contribute to this field. And During my studies at a conference, my current manager from Thermo Fisher has spotted me and I have been recruited. And ever since then, I've been working at Thermo Fisher to help the world safe and healthy and, you know, all that stuff.
Got it. Very cool. What a happy little journey. Big journey, actually, I should say. All right. And Kim, from your side?
Sure. I got my bachelor's at UC Irvine, and that's actually where I sort of started my scientific journey. I was in a laboratory that focused on angiogenesis, so that's development of new blood vessels. And it was really cool. We were studying, or we were more creating like this organ on a chip device. It was very early, and it was like we were gluing together things to make the chips. It was really cool. After that, I have this high interest in like cardiovascular systems of the body. So after completing my time there at UCI, I went to USC to do my master's, and I focused on heart regeneration. And that was interesting because that was where I started my interest in gene therapy. We were looking at a gene that we discovered could help mature cardiomyocytes revert back to immature cardiomyocytes. So the implications would be that if you had heart disease, you had tissues that are damaged from a heart attack and whatnot, that you could revert some of your mature cardiomyocytes and make the immature cardiomyocytes heal your heart. So we were thinking with that gene, that could be a potential gene therapy target, and that is where I tumbled into gene therapy, and where I started like this really big interest in the field. After completing my time at USC, I went on to work at a molecular diagnostic company. Yeah, I still feel like I'm really early in my career. I'm constantly learning, but it's something that I really enjoy.
Did either of you, because both of you kind of have this thread of sort of medicine behind it, did either of you ever consider going to med school, or did you always want to go kind of more of this sort of developing biotech tools and like that type of route? Are we laughing because have I pushed a button accidentally? Is this a sensitive topic?
No, you just started a big rabbit hole for me.
Oh no. Give us a 30-second.
For med school, no. Okay, of course, my parents wanted me to become a doctor. I didn't want to do that because I didn't want to see people in pain most of the time. So I did want to do something with biology because that's something that triggered me. For me, it was like more magic when I first saw science, which obviously, of course, it was on TV. It was on CSI.
Yeah.
And then they do PCR and you find the criminal like right then and there, 6 hours, boom, everybody's caught. In reality, it's not that. So I actually thought about going into forensics before, going into like all science. But then I realized all the tools that forensics use does need advanced technology on the biotech side. And that's when I said, okay, I don't want to be a doctor, but I kind of want to live the life that I see in CSI. But without these tools, I can't do that. So let's make these tools first.
Okay, very cool.
So that's how I came into here.
Way to summarize that rabbit hole. All right. And Kim, from your side?
Yes, big yes. When I first started my bachelor's, I had intended to go to medical school. That was the goal when I first went into college. And I come from a family of everybody's doctors, so that was sort of the expectation for me. But as I was looking around, I joined that angiogenesis lab, intending for that to be on my resume when I went into medical school. Yeah, and at the same time, I was also volunteering at a hospital, so I was doing all the extracurriculars. But while I was simultaneously volunteering at the hospital and volunteering at the lab, I had more fun being in lab than I was in the hospital. So I felt like that was like my flag telling me mentally, maybe I shouldn't be switching my career. And it was kind of scary because I had no idea what this world was like, being a scientist and doing research, going through that career change and kind of changing the directory of where I thought my life was going to go. I think it was a big jump, but I am so glad that I had that experience because I'm here now, and I feel like if I didn't have that moment, I would probably still be trying to get into medical school, or maybe I would be, but I have a lot more fulfillment where I am now. So I don't have regrets at all.
Yay! I love a happy ending. Yeah. I think it's important to highlight, like, it's okay along the career path as a whole to like feel maybe a little lost sometimes or a little unsure of what those next steps look like. And sometimes either life will kind of swoop in and give you something that will show you a little bit more of what you're interested in, or another theme that we've kind of come across when discussing about careers on this show is like the importance of a mentor. And sometimes mentorship can be very, very beneficial too. Do either of you have mentors who have helped to kind of guide you along the way?
How about you take it first, Kim? This is a bigger rabbit hole. I need a longer time to
God,
summarize.
what am I doing to you? Okay, all right.
Why are you
I'm
doing
so
this
sorry.
to me,
This
Cassie?
is supposed to be easy. Okay, all right.
I've had a lot of different mentors along the way. The one person that I sort of still remember to this day was my first PI. He told me as I was kind of making this big decision for myself and kind of trying to convince myself to take the plunge, I think the one thing he said was that his love for science he views as, or his love for research is he views it as this big black void. And as a scientist, you're chipping away a little bit at a time at that void. And there are moments where you'll have something and you're the only person in the world that knows that information. And I felt like that was so inspiring. So that's something I try to remember every time I'm working, and trying to remember those moments where I'm the only person that's holding this information that I got from the black void. And
Neat.
It's something that I've carried with me since then.
Very cool. Minjin, do you have a version of the black void?
Yeah, as like Kim, I do have like a lot of mentors on the way that guided me throughout my career path. Two stands out. One of them, it just stands out because like one sentence he said. And that was when I was at KISS, the Korean Institute of Science and Technology. And he actually told me, oh, you're in science. Great. Now expect that 98% of the time you're going to fail. Just take in that 2%. And that makes me a little happier because it actually happens that way. And when an experiment doesn't go my way, then it's normal. Now I'm fierce if it goes perfectly right at the first try. Like something's wrong. So I think that's a good advice for anyone out there that's trying to pursue a career in research. Honestly, though, 98% of your experiments will fail, and that's normal. But life-wise, my biggest mentor is a mentor that I met in undergrad. He was actually a theology professor. Again, like in the career session, it's really good to be lost. I was lost a lot away from this career path. And that's when he showed me that that's okay. You could do whatever you want as long as you know what you want to do and what you want to be focusing on later in your life. That is okay. He actually gave me the strength to pursue what I think was right for me, even though I had to change the path years in. And I think that's also something that we forget most of the times because we're so focused on just advancing and advancing. Sometimes it's okay to just let what your heart likes to do. Of course, you can't do anything too impulsive, but sometimes it's good to like gear off and explore the unknown for a little bit and then come back. The road's always going to be there for you.
My God, that turned out to be, both of you, like so much more inspiring than I anticipated. Thank you. Yeah, it's true. And it's a brave thing to do too, changing tracks and mixing things up. And I think it's also important to highlight that you don't just have to have one mentor over the course of everything. Mentorship takes many forms in many different ways. So really good points to touch on there. Thank you. Now here comes the doozy question. I ask this question of everybody. Are you both sweating? You should be sweating right now. No, I'm just kidding. It's really not a big deal. So the question is...
I'm sweating and she's not even asking
Jordan's
me the
sweating.
question.
I'm sweating. So the question, now that we've established we're all sweating, the question is, what is, and this is for both of you, What is your most embarrassing lab moment and your proudest lab moment? Minjin's ready.
I have too many embarrassing moments, and I can't pick which one's more embarrassing the other one.
Oh, good.
I know what the proudest. There are two proudest, at least. The most proud moment was when I finally, well, in a nutshell, I got to say "I told you so" to my PI.
Oh, nice. Oh, that felt good.
That was like such a proud. That's my proudest moment for as of now. Kim, why don't you go first before I do my embarrassing moment? There's multiple. One of the moments is like, I didn't do it. My friend, wink wink, wanted something sweet. In lab time, we were working overtime. We were doing cell culture. So he went to the ice machine, got ice, and put syrup on it and ate it. And then 30 minutes later, he was left in the bathroom for hours.
Oh, no. Oh, no.
And I should have probably prevented him. But I said, yeah, go see. I want to see what happened.
Oh, no.
I was a bad friend. I didn't eat it. My friend did. He was in pain. I made up for it. I bought him nice dinner once he recovered. But one thing, that's why if there's any sign saying do not consume for lab use only, you need to follow it, people, okay?
So we all learned a valuable lesson here today. Don't eat the ice in the lab. The end. All right, Kim, can you top making somebody ill?
I don't know if it'll top it, but probably my most embarrassing was when I got pulled out of lab by the police.
What? This is so juicy.
Let me explain.
Okay.
It wasn't my fault. I was about to leave for lab. I lived across the street. I was living on campus, and I saw, like, before I left my front door, I saw, like, in the window that there was a guy stealing stuff from my neighbor. So I was on the phone. I called 911, and they were like, "Okay, we'll go check it out." And I was standing there. I was like, "I need to go to lab." In retrospect, I should have stayed because I was the one that called 911 in the first place. So then I went to lab. I thought everything was fine, and then I got a call as soon as I got to lab saying, "You need to come back in. Why did you leave? The crime scene." I was like, "I'm sorry. Let me go. I'll come back." And they picked me up in the car, but I had to tell my mentor first, my PhD mentor, and he kind of looked at me and he was like, "What did you do?" So, I mean, like, it was in front of everybody too in the lab, so it was just like, I didn't do anything. Police had to.
Did everybody think you were like the coolest for a second? They were like, "Wow, look at this renegade. That's crazy."
Yeah, right. They put me in the back seat.
In the back seat? You had it right in the back?
I was the one that looked like I did something.
Okay, well, we definitely need the sirens. The sirens have to be in this because of this story. All right, then that...
I didn't do it.
Wow, neither of those were what I would have expected. What is happening during Cassie's Career Corner today? We are blowing my mind. What's your proudest moment then? Was it also when you were taken away in a police car in the back seat and you're like, "Wow, I'm so cool right now"?
My proudest moment would be when I first cultured cardiomyocytes and I saw it beating for the first time. Yeah.
Oh, that's cool.
I've cultured cells before, but I got like a rush of excitement seeing the beating. I was so excited. I took a video on my phone through the microscope so that I could like have it forever. So every time I do like an elevator pitch about what I've done in the past, I usually just scroll and show that video of beating cells.
Yeah, you're like, "Hey, want to see something cool?" I would too. I would break that out all over the place.
Look
you're like,
what I
"It's very cool." Wow.
Kim and Minjin, thank you so much for joining us on the podcast today. Some great stories and great insight into some of this research and AAV and LVV. So really appreciate having you on today. Thank you so much for being here.
Thank you.
Thank you for having me. Thank you for having us.
That was Dr. Minjin Kim and Kimberly Gomez, scientists at Thermo Fisher Scientific. Thank you so much for joining us for today's episode of Absolute Genius. It was produced by Sarah Berganti, Matt Ferris, and Matthew Stock, with more great science around the corner in future episodes. Stay curious, and we'll see you next time.
Jordan, you're on fire.
Do I need a fire extinguisher?
I think so.
Is it
Yeah,
my hair?
I
Stop,
think
drop, and
probably.
roll? I don't see anything in the background here.
You need Elsa, that's what.
That's right.
I'll just let it go.
Oh my God.